whereas in titanium diselenide, it seems to be associated with a Fermi surface reconstruction and limited to the charge density wave phase, and hence probably arises due to the charge density wave phonons. Okay, I guess I should hide this bar here. Right. So how can I hide this? Yes, that's good. Let me start with a brief introduction to charge density waves. If I can advance slides, yes, I can. The classical picture, the most classical picture for charge density waves is the Piles distortion, which is taught in textbooks in 1 dimensions, and tells us that it's always energetically favorable for an electron gas to lower its energy by forming a gap due to a potential that is introduced with exactly the wave vector 2kF. And that gives still with that in 1D strictly, it gives a metal insulator transition. In 2 dimensions, one doesn't have this case anymore because one doesn't have a perfect nesting. And one day one is guaranteed the perfect nesting because you've got exactly one Q vector connecting the Fermi level, the Fermi surface points. In 2D, one can have still a charge density wave occurring due to nesting by having one Q vector that maps a reasonably large part of the Fermi surface onto another part of the Fermi surface. In both cases, we expect that there is a coupling to the crystal lattice in solid state systems and hence a visible lattice distortion. For many interesting materials, the nesting that this sketch implies is actually not observed for the Fermi surface, and hence we do definitely need some other mechanisms to be involved as well in the formation of charge density waves. Most notably, there is a potential. Maybe actually let me still go for this. There's a potential for the electron phonon coupling to be particularly strong for a specific Q vector, and hence that could still favor the formation of a charge density wave even when there's poor Fermi surface nesting. We will see that this is certainly part of the picture for niobium diselenide and also for titanium diselenide. In addition, we can have the excitonic charge density wave mechanism by which one forms electron-hole pairs, and these condense into a type of Bose-Einstein condensation. The requirement for that is that the charge density is small because one needs to avoid screening. One needs to retain a finite Coulomb interaction between electrons and holes to form these pairs. Specifically, and one needs to have a small overlap, hence, of electron and hole pockets in a solid to be able to form a excitonic charge density wave. Specifically, this overlap has to be smaller than the gap of the charge density wave, as the binding of the exciton electron hole pairs. There is, in both cases, one can imagine that there might be interactions between charge density waves and superconductivity, and the classical picture is that one has a competition for density of states. This was formulated very early on by Bilbro and Macmillan, for instance. The rationale being that both states require the condensation of electronic states, and hence they gap out electronic states, and hence they are competing for the same electronic states at the Fermi level to form either order. And in most cases, indeed, one finds that charge density wave order has higher transition temperatures. Hence, one can usually imagine that charge density waves would suppress superconductivity. I'll make the case that this is indeed what's happening in niobium diselenide, despite some earlier studies claiming opposite. But I'll come to that in my first part of my talk. In the second part of my talk, I'll be talking about titanium diselenide. Titanium diselenide has been argued to be the one example of a charge, or one of the few examples of a charge density wave which is suppressed to become quantum critical. So here one can see the charge density wave in copper intercalated samples being reduced, and a superconducting dome emerging around the point where this charge density wave is suppressed. So that was prompting this to be analog to magnetic systems like serum palladium-2 silicon-2, where a magnetic transition was clearly suppressed to 0 temperature, and clearly a superconducting dome was observed around that critical quantum critical point. And we've also got, of course, theories that tell us that there is the superconductivity there might be mediated by the quantum fluctuations, the magnetic quantum fluctuations. For titanium selenide, copper intercalation, as I said, has given us this picture. Similar experiments have been done under pressure. I'll discuss them in a bit more detail today, and I will show our results on how the Fermi surface evolves, both the underlying Fermi surface of the parent state as well as the reconstructed Fermi surface in the charge density wave, and then I'll compare that with the presence of superconductivity and argue that it's mostly because of which Fermi surface sheets are available, but nevertheless the charge density wave seems to play an important role.
How can you rule out the effects of phonons from this, which of course inevitably evolve with the charge density wave?
The charge density wave, of course, the fluctuations of the charge density wave, after all, are phonons, and hence one could imagine one can associate the superconductivity there with the phonons. Now the question is it fluctuations around the quantum critical point, or where you would have soft phonons, or is it actually inside the charge density wave where you'd have a finite gap for those phonons associated with the charge density wave? And I'll come to the picture of what's the case in titanium selenide towards the end of my second part. Okay, let me start with niobium diselenide. So here I'll be, as I said, I'll be arguing that there is a competition, and in particular the superconductivity is suppressed by the charge density wave order. On the side, we observe that there is a first order transition in the charge density wave as well. So a little bit of background to niobium diselenide. It's an experimentalist's favorite. It's very easy to grow. It's in particular a favorite for all the STM and any studies that involve cleaving crystals, because it cleaves so easily, and yet has a few interesting phenomena. Namely, for instance, it has got a charge density wave at low temperatures, specifically below 33 Kelvin, and it has superconductivity at even lower temperatures of about 7 Kelvin. The lattice distortion has been clearly observed. So this is the integrated intensity of the satellite peaks due to the charge density wave. The peaks tell us that the Q vector is incommensurate, slightly off 1/3. One can see that the intensity grows towards lowest temperatures, in particular that it's not suppressed by superconductivity, as evidenced here by the fact when you do the experiment in finite magnetic field, which does suppress the superconductivity. So one can see that there's no influence on the charge density wave whether or not the superconductivity is there. The Fermi surface here is, for instance, looked at by ARPES. As I said, it cleaves easily, and hence you probably already guessed that it is a very two-dimensional material. And in fact, there are several barrel-shaped Fermi surfaces, 2 around the gamma point and 2 around the K point, as an additionally a pancake around the gamma point with very small density of states. The charge density wave vector connects 3 points on this inner K barrel. So this triangle here marks the charge density wave vector. And it's exactly there where the charge density wave gap is being observed to be largest and states being gapped out by the superconductivity. This is a small part of the Fermi surface, and hence the effect on the electronic properties is smallish. For instance, in the resistivity, one can only see a very weak bump here at the onset of the charge density wave temperature. It becomes much more visible if one looks at the Hall effect, and that's what we've done in some detail with high pressure measurements. So first of all, in zero pressure, you can see that one can see that the Hall effect is fairly temperature constant over a large range, and then it does have a large drop in fact changes sign at around the charge density wave transition temperature. We've looked at this. So here, these are points extracted from isotherms, but it's much better to do temperature sweeps of the Hall coefficient, which of course involves several temperature sweeps to do the antisymmetric part. The benefit of this being that one can then take a derivative and has got much better resolution. We observe that there is a big peak in the derivative of the Hall coefficient, and as the charge density wave is associated with this change of the Fermi surface, it's natural to associate the largest magnitude in the derivative of the Hall coefficient with the strongest change of the Fermi surface, and hence with the charge density wave transition temperature. And we can indeed see this, follow this here, and I've added points from the Hall coefficient here as blue triangles, as well as those signatures that we've observed in resistivity to this phase diagram. Of course.
So concerning this sign change in the Hall coefficient, is it that the inner pockets, so let's say the gamma pockets and the K pockets are one is Hall, one is electron, and one gets switched off, or is it that really those which are at the K point are going to change the character from the end to Hall?
It depends on how complex, how detailed you look at the Fermi surface, because if you actually calculate the mass tensor or the mass tensor element mxy that's relevant for the Hall coefficient, it varies over several of those. Even within one of those barrels, it varies. So one can't say one is just electron-like and one is just Hall-like. There's Hall and electron character to several of those bands. And hence, it's a bit more complicated to answer the question, why does it exactly turn negative? But on average, the majority of them is indeed Hall-like. And what is likely is that we introduce a very strong curvature of the reconstructed Fermi surface, and it is these highly curved bits of the Fermi surface that always dominate the Hall coefficient. So that's why probably, even though we are doing very little, or even though we're considering only very small bits of the Fermi surface that are kept out, the Hall coefficient can change dramatically from positive to negative. And in a multi-band system like this, it also depends very subtlety with subtlety on the mobilities of the individual bands, so that it's a weighted average. So it's just from the Hall coefficient, it's often difficult to say exactly what's happening to the Fermi surface. But it is a powerful probe of saying that something is happening to the Fermi surface. Now, we can also look at what the isotherms do as a function of pressure, and that's what's plotted down here. And we can see some clear kinks in the Hall coefficient as a function of pressure. You can see that the signature becomes smaller, but from this we can see that there's a quite clear kink associated which we associate with the charge density wave. It's pretty constant outside the charge density wave, and then a sharp drop. And we can in particular see that for 5 and 10 Kelvin, this kink happens at essentially the same pressure. And I've included this here as those black points. For higher temperature, that does shift to lower pressure, in line with what we see from these other probes. And hence we can establish the phase diagram of the charge density wave as being smoothly suppressed and then suddenly dropping to zero. And hence we have evidence here that there's a first order transition of the charge density wave. Down here is a picture of how the sample sits in the pressure cell, but I'll talk about this tomorrow in more detail. Now let's look at the superconductivity. We've done that with measurements of the magnetization under pressure, and we can quite clearly see the Meissner effect in zero field cooled measurements and in small magnetic fields. We have spent a bit of time to work out how this looks like if we prepare samples in different pressure media and with different sample qualities. And we find that it requires the highest sample qualities and highest pressure medium qualities to get this curve, which is now highlighted here in red, namely which increases where TC increases linearly and then quite clearly levels off. Now, if we put this curve for the superconductivity together with the charge density wave, we get a quite clear picture, namely that it's exactly where the charge density wave is suppressed. This is where the superconductivity rises. And once this charge density wave is completely suppressed, the superconductivity is pretty much constant.
Yes,
Yes.
Yes, so I was going to ask, are there any changes in the flux structure of the flux lattice as a function of pressure?
That would be very difficult to answer this question because that requires some imaging methods, which usually is done by magnetic decoration, and sprinkling something magnetic on a sample inside the pressure cell is going to be very tricky. I guess the alternative would be neutron scattering. That's doable. Yeah, that could be done, but I don't think anybody has looked at it. People have looked at the flux lattice at ambient pressure, I'm pretty sure, with STM.
No, I think yes.
And as far as I remember, I don't remember anything spectacular, so I expected that's the hexagonal flux lattice. Yeah, nobody has looked at this, and it's a non-trivial experiment. Is there any particular reason why? Okay. So the comparison of the charge density wave temperature and superconducting temperature already suggests that this wedge of superconductivity here is essentially eaten away by the charge density wave. More clearly, we can see this here, for instance, if we plot TC versus the charge density wave temperature, we see a very obvious anticorrelation in that region where both exist. Not necessarily with the exponential Bilbro-Macmillan law, which would rather expect a logarithmic dependency, but nevertheless, a very clear anticorrelation. And the reason that it doesn't work out with the Bilbro-Macmillan is that it requires to look at the Fermi surface in a little bit more detail. And we've done this. So we've taken the Fermi surface of niobium diselenide. So this is just the reducible wedge here. You can see the two gamma barrels here, the two K barrels here, and we've neglected the pancake because it's got very little density of states. Felix Flicker has modeled now the charge density wave as removing the spectral weight of the Fermi surface where the Q vector connects those pieces of the inner barrel, namely here around these points. And you can see how this, as the charge density wave becomes stronger, removes more and more of that Fermi surface. So note that this essentially corresponds to the smallest pressure, but to the largest charge density wave. And as a consequence, we can simply see that the density of state grows. So the black line here corresponds to the full density of states over all Fermi surfaces given for a specific magnitude of the charge density wave. And we can now simply use the transition curve and convert that into take the BCS ratio to convert it into a gap magnitude. And hence we can use this to calculate the density of states as a function of pressure. And if we use then the BCS equation for superconductivity, we fix it here at zero pressure to obtain an electron phonon constant. And then using the density of states, we get this curve here in gray for the transition temperature. And you can see that it grows very closely to what the experimental values observe. So hence we have a very strong case that the whole physics of the superconductivity and charge density wave in niobium diselenide are essentially can be discussed in terms of what's happening to the Fermi surface and what density of states is available to the superconductivity. The first order nature of the Fermi surface reconstruction, I said already, is visible in the Hall effect, but it is also visible in the superconducting properties that the charge density wave is suddenly completely disappearing. Namely, we observe that the Fermi velocity as extracted from the slope of the critical field, HC2, it does smoothly increase up to the point where the transition temperature of the superconductor is larger than that of the charge density wave, and then it jumps and becomes constant outside the charge density wave. So again, that's something which is sensitive to the Fermi surface and shows us that there is a jump and hence a first order transition of the charge density wave. Okay, so that's my bit on niobium diselenide. So let me now move on to titanium diselenide, unless there are still any questions about this. So for titanium diselenide, we have done ambient and high pressure experiments to study the Fermi surface in quite detail, as well as the influence of the charge density wave fluctuations on the electronic properties. Titanium diselenide is just the same, essentially the same structure like niobium diselenide, and it forms similarly plate-like crystals like niobium diselenide. They cleave a little bit less well, but still good enough. Again, has got a charge density wave, which here has got an onset temperature of 200 Kelvin. It is commensurate, half a half a half. There is, it does connect, hence it does connect the L points of the Browning zone with the gamma point, or many ARPES people will only think about the two-dimensional projection. They will say it's connecting the M point with the gamma point, and but that's of course equivalent views in 2D and 3D. There's also discussions about chiral order and orbital order, but I'm not going to go into that today. What is more relevant is that titanium diselenide is much closer to that, is a good candidate for this excitonic mechanism, because it has got a very small electron and a very small hole pocket. And hence the charge density wave is making a big impact on the electronic properties. So for instance, the resistivity looks very unconventional. Here one can see that it does look even non-metallic at room temperature, goes through a big hump, and then metallic at lowest temperatures. Remember that the transition temperature, charge density wave transition temperature, is about here. I'll look into how exactly that manifests in the resistivity a few more slides down the line. But let me first show you what ARPES measurements have shown us about the Fermi surface and band structure of the materials. So this is all at ambient pressure. At high temperatures outside the charge density wave, one does see just a little bit of the titanium electron pocket here, as well as all of the selenium hole pockets around the Browning zone center. As one cools down, and these pockets at the L points, one can see they are elliptical around the L point. As one cools the sample to below the transition temperature, one can quite clearly here in ARPES see the charge density wave gap, and one can see the reconstructed Fermi surface gives a circular Fermi surface, at least in this two-dimensional projection. The fact that this is now appearing at the L point is an effect of the ARPES matrix elements, but it is equivalent to the gamma point in the reconstructed Fermi surface. So the picture fits quite nicely with what I've had on as a sketch early on, in that there's not good nesting in terms of the topology of the Fermi surface, but it does fulfill all the criteria for excitonic mechanism, namely that you've got a small electron and hole pocket. Whether or not there's overlap or a direct or a gap between them, that's ARPES gets that wrong, I think, and I can show you how we can see that. But it doesn't matter too much. It's a small overlap compared to the gap, and hence we can quite clearly see this gap emerging here. So it tells us that excitonic superconductivity as charge density wave is possible, and indeed some ultra fast experiments also see time scales associated with excitonic mechanism contributing to the charge density wave.
It's very close to being a topological insulator. The system with the P, with the overlap of the D and the P at the gamma point. Any difference on the physics?
Doesn't that require it to be doesn't that require it to be pure D and pure P protected by symmetry? I don't think that's the case in the presence of spin orbit here.
No, I think it just requires them to have opposite parity, which they clearly do have.
But doesn't it need to be pure parity states in each band then, for it to give us a topological?
It's really, if I thought it occurred at the gamma point, so
the D band exists at the L point, and the P band exists at the gamma point. So they are not at the same point in reciprocal space.
But in the reduced
In the reduced zone there are, but then they're already hybridizing with each other.
Good.
Okay, maybe we should pick up on this. I thought that I thought that it wouldn't be enough, but
well, I don't know what the counting is, whether it counts as an even or odd number of crossings, but first sight looks like it's an odd number. So that if it did become an insulator, it would probably be topological, but I don't know.
okay, maybe we can discuss this later. I thought that it's not strong enough for being a topological insulator, but maybe I've got that wrong.
Okay, well, okay.
Could you review again, sorry, I didn't quite understand, how you would tell the difference between a CDW that's electron photon compared to excitonic? You have to know about, you have to do ARPES to do that, or is there some other way?
The best, so far the best ways, and that's what Hellman, for instance, did, is to look at the how fast at the response times of the melting of the charge density wave. So by sending in melting the charge density wave with a short laser pulse and then looking how it reestablishes itself, one can see whether that's picoseconds, which would be possible for electronics, sorry, femtoseconds, possible for electronic mechanisms like excitons, or whether it's picoseconds, which you would associate with electron phonon. And both are present and have been observed in several experiments. So hence the association is that both electron phonon and excitonic mechanism contribute to the charge density wave here.
But the actual charge density wave itself, in terms of bulk measurements, you can't tell.
I don't think that there's a way that bulk measurements can tell whether or not it's static bulk measurements. I don't think they can tell whether it's excitonic. They can, you can establish whether or not the conditions are fulfilled, but probably not. I don't see how it can establish whether or not it is indeed in the end an excitonic.
Okay, thank you.
You know if this is a 3Q CDW or unidirectional in the twin?
It is 3Q, and I'll establish evidence for that later on as well. But this particular reflection peak 3.5 is would not have intensity. I think if it was just 1Q, then you would go at 1/2 0 0. Okay, so this way we've looked at two snapshots of the electronic structure. Let's look at how it evolves from this limit to that limit. So we're going down in temperature at 0 pressure for now. We've done that with transport measurements. Here's the curves of the hole resistivity and the longitudinal resistivity. We have fitted these with a two-band model where, of course, we've got four parameters: an electron hole concentration and mobility each. However, we fix one of them by observing that the total charge carrier concentration is fixed by whatever. That's a little bit dependent on impurities that are on the system, and there's a discussion going on whether one would have the Fermi level in perfect crystals in the gap and hence a perfect insulator, but pretty much so 95% of all groups that make titanium selenide do obtain crystals with a slight electron doping. So did we, and hence we fix this electron doping. We determine it at once at lowest temperature, and then we fix it for all the fits of our two-band model. The important result is that we can now follow the carrier concentrations and mobilities as a function of temperature. We observe them to be weakly temperature dependent above the charge density wave transition. This is simply associated with thermal occupation because it's very small pockets. So the Fermi energy is small, is comparable to the temperature, and hence we get some thermal occupation already relevant up here. But then most importantly, we get a very strong decrease at the charge density wave transition temperature in both electron and hole concentration. So that shows that the Fermi surface is reconstructed, that we lose pretty much all of the holes and have a small electron concentration left at low temperatures. We can also see that the mobilities on each band have got a minimum at the charge density wave transition temperature. And that tells us that there is strong scattering of the charge density wave fluctuations dominating there. Indeed, it maps exactly what's been observed in inelastic scatterings. We can also analyze the magnetoresistance in a little bit more detail. In particular, we can observe that the magnetoresistance plotted versus magnetic field divided by zero field resistance squared does obey Kohler scaling at high temperatures. So there's two curves here as an example for high temperature, which fall on top of each other. But then the moment we go through the charge density wave transition, they do wander off and then come back. A better way to look at this is to actually just look at the slope of these curves. And we can see that the slope of these curves, that's these red points here, is constant above the transition temperature and then shoots up in the charge density wave transition temperature. And indeed, again, this tells us that there's that this is sensitive to the Fermi surface reconstruction, because the magnetoresistance is a product, is an integral of the mean free path around the Fermi surface, where the local Hall angle enters in here, and both the mean free path as well as the local Hall angle are, of course, the local Hall angle is sensitive to how the Fermi surface looks like, how the curvatures look like and everything. The mean free path, of course, is sensitive to any changes in scattering anisotropy. So we can't tell whether the magnetoresistance is picking up the Fermi surface change via the Hall angle or whether it's picking up the scattering anisotropy change via the mean free path, but both of them are expected to change at the charge density wave transition. So it's quite clear that we can expect some sensitivity here. And I'll continue to use this tool of the magnetoresistance through our high pressure studies as well. So we've established very well that there is a Fermi surface reconstruction. Now let's see whether we can confirm what ARPES see, whether we can confirm that with. That was 10 Tesla, these magnetoresistance. Oh, sorry, this is the slope of magnetoresistance curves. So it's from 0 to 14 Tesla, and there are just straight lines in those Kohler plots. Inside the charge density wave, I've already shown that picture for the ARPES, which sees these circular Fermi surfaces in the two-dimensional projection. In quantum, we do observe quantum oscillations in high magnetic fields in titanium selenide. You can see them here in the resistance. Fourier transformation gives us a frequency of about 300 Tesla. And that indeed matches very well with the size that ARPES is seeing here. In addition, we can measure the angular dependence. So that's what's plotted down here. And we can fit this with an elliptical Fermi surface with an in-plane isotropic profile and an out-of-plane longer Fermi vector. That ratio, once we've got this fitted, tells us essentially what that Fermi surface pocket looks like. We can then calculate using the effective mass that we've also measured in quantum oscillations. We can use this to calculate the specific heat, and that indeed that what we get here from quantum oscillations agrees exactly with what specific heat measurements have measured. Hence, this thermodynamic police tells us this is the only Fermi surface that we observe. So it tells us that this picture, and it of course also fits with our Hall effect measurements that I've shown 2 slides earlier, which also give us a Hall coefficient that's in perfect agreement with this. So it tells us that we essentially see everything with transport measurements in titanium selenide at 0 pressure. Now let's see what happens as we apply pressure, because that way we get closer to the superconductivity. And the answer is that quite a lot of changes. So we've had this 0 pressure curve with this dramatic peak, indicating that essentially pretty much all of the Fermi surface is gapped out. This peak becomes much weaker, and in fact, here at a pressure of 1.5 GPa becomes more prototypical of what one expects for the charge density wave in a partially gapped system, namely a hump. This hump weakens more and more, and eventually we can only trace it in the derivative as a very weak signature. But this way we can establish the charge density wave temperature over a large range of pressure. We also use the magnetoresistance measurements again. So here I've got now curves of the magnetoresistance recorded at a fixed field as a function of temperature. So temperature is now an implicit parameter in these plots. So here's the magnetoresistance versus B over rho naught, and rho naught is the parameter that varies with temperature. You can see that there is a change of slope, for instance, here in this purple curve. Change of slope is best always analyzed by taking a derivative of the curve, and that's exactly what I've done down here. So you can see here a peak in this derivative. And now I'm transforming these plots. Having taken this derivative, I can now transform these plots back into versus temperature. So I take the slope and here plot it again, temperature again. And now you can see more clearly what happens, namely that the slope is constant at high temperature, and then there's a sudden rise, and then some smooth behavior again at low temperatures. The sudden rise is exactly what we associate again with the charge density wave. We had that already at zero pressure, and we associated with the Fermi surface reconstruction, and that gives us a few more points how we can follow the transition as a function of pressure, and we establish hence this full phase diagram here.
What is the configuration? Is it that the transport is in the plane and the field is perpendicular to the plane?
That's correct, yes.
Okay, and the pressure is hydrostatic?
Yes.
Okay. And can you put uniaxial pressure? Or what
You can, and that leads to quite some differences. So for instance, if you look at these points here in orange, they have been done previously by another group using a different pressure medium, which is not hydrostatic. In fact, it is solid, it's steatite, and that clearly will produce more compression along the z-axis than in the plane. And what one can observe is that the charge density wave is suppressed quicker this way, and it is also, the signatures are lost much quicker. So of course, it's not a very controlled way, and it's very difficult to do this in a controlled way, that you've got a uniform uniaxial pressure is extremely difficult to establish. I wouldn't actually know how one would want to do it on the slide. So that washes out signatures, but it also suppresses, the clear message is that uniaxial pressure suppresses the charge density wave quicker. Okay, so with that, we've now established that this charge density wave is suppressed. We've essentially also looked a bit at how different pressure media can influence this. So clearly the message is one needs as good a pressure medium as possible to really see the intrinsic behavior. Our study used glycerol, which is slightly worse than methanol, ethanol previously used by Joey et al. And you can see they've already got a higher critical pressure. One could now speculate that in a perfect conditions, one might even get a full linear dependence of the charge density wave temperature over the full pressure range, which is indeed what one might expect in 2 dimensions for the critical exponent of the charge density wave, because the critical exponent there is 1. Right, so we've now looked at the Fermi surface at high pressures in more detail. We've seen quantum oscillations at ambient pressures, so there's clearly an interest to see what they do as a function of pressure. And here are a few traces. So at low pressure, we see this one small frequency, but already at intermediate pressures of 2 GPa, we see additional frequencies coming up, and we do observe more and more frequencies coming up at high pressure. In these Fourier transforms, we can trace some of them quite clearly. In particular, this new high frequency here starts out at 2 kilotesla and increases up to above 3 kilotesla at 6 GPa. And a few more details are happening down here. We can, of course, plot these frequencies versus pressure, and I'm already including on this slide these experimental points here in black, as well as what DFT can teach us about the material. And indeed, DFT, with a few adjustments, for instance, adding an extra bend shift, and we can get the Fermi surface, and we can understand the Fermi surface quite well outside the charge density wave. So you can see outside the charge density wave, we've got a perfect agreement here for this largest frequency, as well as for these two smaller frequencies. This large frequency is the belly of this Fermi surface. This medium frequency is the belly of these pockets around the L point, and this lowest frequency is the belly of this inner gamma pocket. Now, inside the charge density wave, as you expect, the Fermi surface is reconstructed, but actually the experimental points of this highest frequency carry on quite some time into the charge density wave and only are lost at about 2 GPa. Now, DFT is not predicting us, probably not too much a surprise to you. And DFT also gets it wrong in the limit of zero pressure, in that it tells us that there would still be a large pocket from this Fermi surface. And we've now set out to model this in more detail, include the charge density wave, because this DFT model does not include the charge density wave. So we've developed a tight binding model, which takes 2 selenium bands here, as well as the threefold degenerate L band. And we consider the hybridization of this L band, of this titanium band, with the selenium bands. So essentially it corresponds to mapping all these titanium bands onto the gamma point, onto the zone center, which establishes, you can see this here, down here, this flower shape. And then switching on a hybridization between selenium and titanium states, but never between titanium and also not between selenium states. This way we can establish that we form a circular Fermi surface at zero pressure, which is in agreement again with all those measurements I've shown you already. And here you can see how the hybridization acts. So we've had 2 clear hole bands, which now hybridize with these 3 copies of the electron band, all shifted to the gamma point, but rotated to each other. So we have considered these to be elliptical with two axes of the electron mass, and rotated to give us this flower shape here. Now, the result of this is that the frequency versus pressures are now very well understood, and most importantly, this highest frequency, which is of course the largest Fermi surface and hence the most important, we capture the fact that this frequency disappears exactly at 2 GPa. So our tight binding results are the solid lines here, and the points are the experimental points.
What happens at 2 GPa?
I'll show you an animation on the next slide. We also observe this reconstruction here at the critical pressure, but essentially at this pressure we have a Lifshitz transition. So I hope that this will play now. Yeah, so I'm now playing this animation through as pressure varies, and you can see that the flower shapes here, they grow, and sorry, the Fermi surfaces all grow, and the gap becomes smaller, and hence right at the Lifshitz transition, we for the first time observe the outer orbit. Let me replay this. So you can see already the flowers are underlying there, but they don't yet form a Fermi surface. They form disconnected pockets, but now they, for the first time, form this connected outer orbit, and that's where this largest frequency appears. There are 2 different bands, sorry.
You just stick in the delta of P by hand, right? And you make some assumptions of the pressure.
The delta versus P, we take essentially again the transition temperature and scale the gap with the transition temperature.
Oh, okay.
And we've tuned the delta at zero pressure. No, actually, yeah, we've taken the gap at zero pressure from the ARPES measurements at 70 millielectron volts. And then, yeah, we've scaled it with the transition temperature. Can I actually go slow? So, get my. So you can see, if I'm playing this again, you can see that here just before this, I can't stop it. You can see that just before the critical pressure, the the pockets there were still disconnected, and it's at this Lifshitz transition of 2 GPa is where the largest Fermi surface is for the first time continuous, and that gives us this large Fermi surface. And once we're out of the charge density wave, of course, we recover all the original Fermi surfaces, namely the electron bands around the gamma point, as well as the hole bands around the gamma point, as well as the electron bands around the zone corners. Of course.
So you mentioned so far we had the indication sensor incommensurate.
Yes, I'll come to that on the next slide.
Okay, but here this model is always commensurate, right? Because
That's correct. There is evidence in X-ray scattering that there is some incommensuration happening above 4 GPa, so it does not coincide with that Lifshitz transition. It's at a higher pressure, and on top of that, the incommensuration is only in the C direction. It remains commensurate in the plane. Our model is in fact two-dimensional, which captures all the orbits and Fermi surfaces that we observe. So with this incommensurate commensurate transition. So let me first of all highlight where we do observe the superconductivity, or actually other groups have observed it. The superconductivity was observed to start exactly at 2 GPa where this large Fermi surface emerges. So it tells us again that it's living probably on that largest Fermi surface. In that previous study, it was shown to stop at 3.5 GPa. And that's exactly where this X-ray scattering study by Joy et al. Found evidence for the incommensurate charge density wave to exist above this pressure. So that's one possible explanation why the superconductivity is then disappearing there. The other possible explanation is that it was due to the non-hydrostatic conditions in the pressure medium in that study, which looked at the superconductivity. So there's some interest to check this again with a hydrostatic pressure medium. The fact that it is emerging inside the charge density wave and absent outside the charge density wave phase suggests that it is one of the phonons that is reconstructed by the charge density wave is crucial in the superconducting mechanism. So that's why I think there's evidence that it is not related to the quantum criticality of the charge density wave itself, but rather to the phonons that are reconstructed inside the charge density wave. Okay, so with that, I'll finish here. So we've seen the charge density wave and the interplay with superconductivity in both titanium diselenide and niobium diselenide, clear suppression in niobium diselenide, a charge density wave that hosts the superconductivity in titanium diselenide on one of its Fermi surface pockets, and probably linked to the charge density wave reconstructed phonons. So with that, I'd like to highlight a number of people. Actually, I already realized that one important person is missing on the slide, namely Ruma Hin-Loppen, who has done many of the Fermi surface calculations of titanium diselenide, together with Felix Flicker and Jasper van Weetzel, who've implemented the tight binding models, both for titanium diselenide as well as niobium diselenide. Crystals were grown in Bath by Enrico Dacoma and Charles Sayers. Many of the experiments involved high magnetic fields at the HFML in the Netherlands, where Alex and Femke helped us. And yeah, quite a number of people of my group in Bristol were doing a lot of the measurements, both in high field facilities and in Bristol. All right, with that, I'll finish. And yeah, I'm happy to answer more questions.
So, more questions?
So in the niobium, it's kind of releasing degrees of freedom rather than fluctuation driven, wouldn't you say?
Yes.
Yeah.
There have been previous studies which saw kind of a dome of superconductivity, actually with a maximum outside the charge density wave, and have interpreted this as an evidence for quantum criticality. But I think we've looked at this because we've had different results. We've looked at this for several samples with different pressure media, and we quite clearly establish this behavior for the cleanest conditions.
What's going on in titanium diselenide? Because it's not at the critical point, it's somewhere in the middle.
Yes.
Why should the phonons or the fluctuations like switch on at that particular pressure near the end?
For BCS superconductivity, the electron phonon function actually doesn't necessarily want just the lowest energy phonons. It wants, in fact, some of the lowest energy phonons can act pair breaking. So it might be that this is a sweet spot in terms of having the charge density wave reconstructed phonons at the right energy to give you a good electron phonon spectral function, and hence a larger lambda.
It would be nice to see that coming out of quantitative theory.
Of course, yes. So for that, one needs to look at the phonon spectrum in a bit more detail. Yes.
Is it maybe possible to change the size of these small pockets that give you the excitonic mechanism, and see how this influences the CDW as well as the superconductivity?
We do this as a function of pressure. The DFT as well already captures this, that the pockets grow at zero pressure. So you can see these frequencies here increasing. This tells us that this is exactly all these Fermi surfaces growing, and we're definitely going out of that regime where we're going out of that regime that is required for excitonic charge density waves. So we certainly are not in an excitonic charge density wave anymore at 2.5, 3 GPa.
And this could explain then the change from commensurate to incommensurate in principle. I mean, the excitonic seems pretty commensurate to me.
Yes.
Something else needs to come in, and maybe this competition is what ultimately helps the superconductivity.
Okay. Yeah, I've not yet thought about that, but that may be
the
the
dome
case.
is peaked at around where you charge, where you start to become commensurate.
Whether it's peaked there or whether it actually is already the incommensurate transition marks the. One can look at this, either it's being peaked there or it's the moment the incommensurate transition charge density wave exists. It could also mark the suppression of the superconductivity. So.
I have a question for the statement. Superconductivity emerging with the answer of this in pockets. Is it in thermodynamics? Does it look very BCS-ish, or is there something you see like? So the question is obviously, since starting popular,
So
in the pocket. So assuming that the selenium pocket is the one which is most important,
you would want to, and so the experimental probes that you would probably suggest is to look for something like preformed pairs.
Yeah. Or just So for example, how does specifically look like?
At high pressures, that has not yet been measured, because the superconductivity only exists at 2 GPa. Above 2 GPa, that's not completely, that's not trivial. It can be done, but it's not trivial. Maybe at the lowest temperatures that are required here, it might be challenging. So I can't answer that question. That has not been measured. In terms of, I don't think that there's any experimental probes that can answer this question. So that's something that has not been measured yet.
But you said with uniaxial strain, you could destabilize much quicker. So maybe then you could.
The charge density wave is destabilized much quicker. That's true, but
perhaps you can get superconductivity as well. I mean, if you just use C-axis compression or something.
that's worth looking into. That's true.
Probably you don't want to break the in-plane symmetry.
You don't necessarily do this because it's most likely these early experiments actually introduced a compression along the C-axis, which does not break the symmetry. It will induce disorder and dislocations very quite quickly. So yeah, it's maybe not absolutely trivial, but one could look into that in a bit more detail. Yeah.
Yeah. Given the Q is half. Once it's established, in essence, the D states and the P states are on top of one another.
Yes.
In the folded for unknown. And I would have thought that the hybridization would have to vanish at momentum equal to 0 because of the different spatial paritives of the two orbitals. Not entirely sure about this, but I wonder whether you thought about momentum dependence of your hybridization.
So our model does not take that into account. You've seen that we've just put in a constant delta, which only varies as a function of pressure, but has no structure in K-space. And it explains the Fermi surface quite well. So that suggests that there is no.
Well, but the Fermi surface is at finite momentum. It's not at the gamma point. So
yes, that's true.
So it doesn't have to probe with that aspect. It just that seems to me that when you do this the symmetry in the folded crystal structure, that you will have, since there'll be inversion symmetry there will be well-defined parities. Therefore, it must vanish at P equals 0.
Yeah.
But I don't know. Maybe P dot sigma or something. I don't.
Is that still true even in the presence of spin-orbit interaction?
Also spin orbit. I don't know. Is it 2 Kramer's doublets? Are they Kramer's doublets? What I suppose so, right? So
I don't know the details. No.
I have to look at it more carefully.
Yeah,
So
but actually you do get selenium and titanium. So you do get the selenium hole band and the titanium electron pockets even without the spin orbit. So that's not inverted by spin orbit.
Oh.
Isn't that what's required for it to form a topological insulator, that you get an inversion due to spin orbit? And that's not the case here. It's already that way without spin orbit.
Well, an inversion is an inversion. The spin orbit would be required to drive it topological.
Okay.
I suppose. But maybe because of the Q vector I've got it confused, but I just put it to you as a question. Anyway.
Yeah, I can't answer this question. I will have to. I thought that it doesn't qualify, but maybe I'm wrong, and maybe.
And certainly, as a finite Q vector out, if you really were to put them on top of the L points, then of course there's a well-defined, I don't know, inversion symmetry there too. So it seems to me that inversion symmetry dictates that they can't mix at P equals 0 once you double the unit cell. But I'm not entirely sure. And there's this, it's a question of whether, I don't know. Yeah.
You do need the inversion symmetry in real space as well, right?
Yes. Inversion symmetry is inversion symmetry.
We do have it in recipe. I'll have to look at it.
Once it's folded over, it doesn't know that it's not an inversion symmetric.
Yeah, I see your point. I thought that it doesn't qualify, but it seems like I might not have thought it all the way through. I'll have to
share your uncertainty, but just raise it as a question.
Yes, yeah. It's something we need to sit down and look at it more carefully. Yes.
Yeah. Anyway, I think we should thank Sven again.
Thank you.